What is up, YouTube? Let's learn about the OAuth framework and its role in API design. So let's get into it. So to introduce this, we'll explore a popular framework that builds on top of the security protocols we mentioned previously and extend them to implement authorization, which is what the user has access to. This framework is necessary because protocols we studied earlier, such as HTTP authentication, API keys, JWTs, by themselves are not sufficient and have limitations such as using API keys as a standalone authentication mechanism isn't sufficient because they require a solution for their secure transmission, and repeated transmission of tokens for authentication increases the probability of interception by an attacker. And these and other issues require that frameworks embed individual protocols to formulate a complete solution that is able to achieve security goals effectively. A benefit of having a standard authorization mechanism is that security experts can vet out complex issues instead of everyone inventing their own solutions that might have bugs. One of these frameworks is OAuth 2.0. And OAuth 2.0 is a shortened name for Open Authorization 2.0, and it is the preferred way of authorizing access to an API. It's a technological standard that allows applications to access resources hosted by other web apps through an API on behalf of a user. So what is OAuth 2.0? OAuth 2.0 is an industry standard implementation of token-based authorization that was developed through a collaboration between Google and Twitter in 2010. It's built on top of OAuth 1.0, which was developed in 2007. Using OAuth, we can allow access to specific information to API clients without exposing the user's credentials. This information can be used to create accounts on third-party applications without the need for sharing sensitive user credentials like passwords. OAuth does this using access tokens instead of passwords. An access token is an entity that is required to access protected resources. Access tokens are usually encoded as JWTs. An example of its payload is given below, so it kind of looks like a JSON object. Access tokens are used because authorization, which is what the user has access to, is provided for a limited time to specific resources only. User account information is shared without the transmission of authentication information, such as passwords, to any third party. As a real-life example, assume we want to create a new Spotify account using our existing Google account. Spotify allows us to sign up using the Sign Up with Google button. Spotify and Google facilitate this functionality using the OAuth 2.0 framework. So as you can see in the picture, we have a Sign Up with Google button. So firstly, the user initiates sign up on Spotify using their Google account, and then Spotify requests information from Google, and then Google asks for and receives the user's permission to share its information, and then information is then provided to Spotify, and then the account is created with the information it receives. And access to resources requested in the API calls is provided based on the validity of the access tokens. So let's talk about actors and roles. There are 4 entities in the OAuth communication to achieve secure transmission of resources. So firstly, we have the end user. So this is the application user that owns the resources, like the user credentials. And then we have the resource server. So this is the server that holds the resources of the end user, like the Google server holding the user's protected information in the example before. And then we have the application or client. So the application or client requests the user's resources from the resource server, so the Spotify application. And then we have the authorization server. So this server provides authorization to the application or client for accessing the resources like the Google authorization service. So now let's talk about flows. OAuth uses access tokens to allow access to protected resources. Depending on the use case and the actors involved, OAuth facilitates 4 different kinds of communication patterns to obtain the access token. These patterns are referred to as flows. So let's describe each flow. First, we have the authorization code. This is the flow depicted in the Spotify example, where the user logs in and provides the required permissions. After that, a code is obtained to give the user the required permissions. This code is ultimately exchanged for an access token, and the access token can then be used while making the API calls. Then we have authorization code with proof key for code exchange, or PKCE. This is an identical flow as the authorization code, but it has additional security methods. it has an extra parameter called code verifier, which is authenticated before the API server responds to requests. Some applications like Facebook allow us to use PKCE code flow in their APIs for extra protection. Then we have client credentials. These are differentiated from the other flows because no permissions are needed from the end user. The access token is obtained with the client's credentials. This flow is used by applications to access their public resources such as public playlists and the music applications like Spotify. Then there's implicit grant. This is similar to authorization code flow but has no intermediary code. Instead, we directly get an access token that has a very short lifespan and an inability to be refreshed. Nowadays, it's not recommended to use the implicit grant flow because without the intermediary code, the access token can be intercepted. So let's talk about authorization code flow. The authorization code flow is used to distribute access tokens to those applications communicating with a server on behalf of a user. The Spotify example earlier follows this flow. The end user is required to log in and grant the required permissions, after which an authorization code is generated. We can use this code to get an access token, which can then be used to request data. This flow drives the communication between all four actors. So let's understand the communication flow before describing it in detail. So firstly, the application redirects the user to the authorization server. The client or application sends the user credentials in this request. So it sends the client ID, the scope of the request, etc. And so basically you can see in this picture the request sent by the client, and we have the server URL, the format of the response we expect, the ID of the client machine, the client URL, and the access being requested by the application. Then secondly, the authorization server prompts the user to authorize the request made by the application after the authorization server validates the client's identity. Then the user approves or denies the request. After acquiring permissions, the authorization server sends a reply back to the application. The reply contains their authorization code. Its sole purpose is to be traded for an access token as a query parameter. And in the picture, we have an example of an authorization code. The application can then use this authorization code to request an access token from the authorization server. And it's important to note that the authorization server only authorizes the application. The information the application requests is stored on the resource server. And the authorization server sends the access token to the requesting application. So in the flow, the authorization server acts as an intermediary between the end user and the application. The authorization server prompts the user for permission, through which the user logs in and grants the required permissions. Note that in the example of before, the authorization and resource servers belong to Google, whereas the application is Spotify. Why don't we send the client the access token in the first step instead of exchanging it with the authorization code? Directly providing the client with the access token is considered insecure. To exchange the authorization code for the access token is a step added for additional security. If we consider a situation where the access token is sent to the client instead of the authorization code, it'll be returned as a URL parameter, which is stored in the history of the user's browser, leading to vulnerabilities. People can exploit this saved access token. Now let's talk about authorization code with PKCE. The standard authorization code assumes that the client devices could securely store long-term secrets and ignore man-in-the-middle attacks. PKCE extension takes care of these shortcomings. PKCE is the same flow as the authorization code but is considered more secure. PKCE was developed to address the weaknesses of the standard authorization code flow when used by public applications. Public applications aren't deemed trustworthy to hold sensitive user information because it's vulnerable to jailbreaking and stealing with malicious code, etc. Because of this weakness, further security measures are taken to prevent authorization code interception, through which attackers can obtain access tokens and imitate the legitimate user. PKCE extension mainly functions with native mobile applications and single-page applications or SPAs because they're public applications. Let's suppose we have a mobile application that is requesting data from an API. It's imperative for mobile applications to use the PKCE extension. This is necessary because an attacker app has the capability to impersonate the mobile application. The attacker can exchange the authorization code for the access token and impersonate the legitimate user. This is mitigated with the use of PKCE. PKCE is an additional layer of security on the previous OAuth flow. The standard authorization code flow works for confidential clients who are able to store user credentials, which public applications can't. More and more APIs are adding PKCE due to its further security capabilities. So this flow contains two additional elements. Firstly, the code verifier, a randomly generated string only known to the application, and then a code challenge, which is an SHA 256 hash of the code verifier generated by the application. When the application requests the authorization code from the authorization server, it computes and sends the code challenge, which is stored at the authorization server. So firstly, a code challenge is sent along with the user credentials and is stored on the authorization server. Then the authorization server asks the user to grant permissions, and then the user grants the permissions, and the authorization code is sent to the application and redirects the user to the redirect URI. So the authorization server returns the authorization code to the application just like the standard authorization code flow. And in the access token request, along with the authorization code, the application sends its code verifier in plain text, which is a safe transmission due to TLS. And the authorization server performs its own SSJ 256 hash on the obtained code verifier and compares it to the code challenge it has already stored. If they match, the application has proven its identity and an access token will be granted. So here in the picture, the access token requested by the application along with the code verifier. And even if the attacker has the authorization code, its hashed code verifier and code challenge won't match, successfully mitigating this breach. So in the picture, the access token is granted after the two hashes are compared. Now let's talk about implicit grant flow. Before the creation of the authorization code flow with PKCE, the implicit grant flow was used by public applications to obtain access tokens. Now it's used in an environment where application is completely trusted with the user's resources. In the current API landscape, the implicit grant flow is losing favor to the authorization code flow with PKCE. Implicit grant flow functions similarly to the authorization code flow, but instead of getting an authorization code, we get the access token using this flow. However, the tokens have a very short lifespan and cannot be refreshed. This flow isn't recommended due to the risks accompanied by returning the access token this way. So, firstly, the application or client redirects the user to the authorization server, and then the authorization server asks the user to grant permissions, and then the user grants the permissions, and then the access token is granted instantly. Now let's talk about the client credentials flow. In a situation where we don't need to access any of the user's resources, we can obtain the access token through the client credentials flow. This is used to access public endpoints and APIs which don't require user permissions. An example of this is Spotify displaying a public playlist available across the application, so no user permissions will be needed to view the playlist. The application requests tokens from the user and receives them without any communication with the user. So firstly, the application requests the authorization server for the access token, and then the access token is granted. And with no special user permissions required, the access token is exchanged fairly quickly. Through this token, the application can access the desired endpoints. So let's talk about the use cases for the four flows. The situation or optimal use case in which the four flows can be used are detailed in the table below. So if the client is a web app executing on a server, then authorization code or PKCE are good choices. If it doesn't require user permissions, then client credentials is a good way to go. If it's an SPA or mobile app, then authorization code with PKCE is a good way to go. And the application is absolutely trusted with the user's resources, then implicit grant is the way to go. But if PKCE is not possible. So in conclusion, the table below summarizes the differences between the various flows. So for authorization code, it requires users' permissions, it can access or modify users' resources, it's refreshable. Authorization code with PKCE, it requires user permissions, it can access or modify user resources, it is refreshable. Client credentials doesn't require user permissions, it can't access or modify user resources, it's not refreshable. And then for implicit grant, it does require user permissions. It can access or modify user resources, but it's not refreshable. Throughout this entire process, OAuth 2.0 only serves as the authorization what the user has access to framework because nowhere on the access token does it specify who the owner is, so a malicious user could obtain and abuse this access token. If implemented alone, the question of authentication, verifying who the user is, arises, so we tend to pair OAuth 2.0 with a relevant framework to handle these use cases. The actual authentication of the client is usually done through OpenID Connect, which we will explore next week. Thanks so much for watching. This was a topic I was really curious about and had heard a lot about, so I was really excited to do the research for this video. And if you enjoyed it, leave a like and subscribe. If you have any questions, leave a comment, and I'll see you in the next one.